So what I'm saying is, what I'm applying is every physical dimensionality, length, width, and depth. The fourth 90-degree angle is the actual density. We define it as density, but that is the fourth value of spatial retention. Because, hello, and welcome to another episode of My 2 Cent. My name is Paul Emerson, and I'll be giving you my 2 cents. Today's topic is going to be the fourth dimension explained. I apologize for looking exhausted. I am exhausted. I've been working a lot. I'm an active duty enlisted soldier for the Army, and they work us a lot. So we're going to have to just ignore the fact that I look like I need to go to sleep because I just woke up. And this is the only time of the day I have to actually get videos out. I've been falling behind on my schedule because I've been doing a lot of stuff work related. But this topic has been on my mind for a while, and I want to just power through it and get ready for work. So, fourth dimension explained. I have come up with an analogy to elegantly and perfectly explain what the fourth dimension is, and I'm going to share it with you guys right now. Now, I'm going to be using the term retention. I'm going to use retention because I like multiverse theory. One of my favorite subjects and one of my favorite thought experiments is multiverse theory. When I was younger, in my early 20s, I think like 22 or 23, I was trying to figure out how the universe could be a parallel universe or a multiverse or omniverse or an omni-existence as the scale progresses up for me. And one of the things I remember specifically was sitting down asking myself, how do you explain what another universe looks like? How do you describe that? And at that time I didn't have an answer. But over the decade, I've come very close to explaining other dimensionalities. So I'm going to switch from the use of the term dimension to the nomenclature that I like to use, which is retention. I prefer to say retention. So instead of using dimensionality, because it implies spatial dimensionality, which is what we're going to discuss now, I prefer retention because retention for me better conveys higher dimensions, higher geometric spatial dimensions, and higher temporal or time-based dimensions. And instead of saying time-based dimensions, I say time-based retentions. Space-based retentions, time-based retentions. So you can have an infinite number of spatial retentions, you can have an infinite number of temporal retentions, and then you can have an infinite number of higher retentions, which is what we're going to discuss. So that's just for me, for my 2 cents. For my 2 cents, as the videos progress, I will stop using the terminology of dimension, and I will go strictly into retention. So this video technically should be titled The Fourth Retention Explained. But if I title it The Fourth Retention Explained, then the YouTube algorithm won't bring it up as, well, maybe I will title it Fourth Retention Explained. We'll see what happens. It'll probably kill the video. I probably won't get any views or any hits. But maybe that's going to be better. So, we need to establish what spatial retentions are. Spatial retentions are the length, the height, and the depth of our universe. So our universe has three-dimensionality, right? All objects. I don't have a box or a cube. So the actual physical geometry of our universe has 3 dimensions. Even if I was to show you a sheet of paper, because this is what is usually used to illustrate 2-dimensionality, there is a thickness to this paper that can be measured. We have a measuring device that can measure the thickness of the paper. So the easiest way to understand dimensionality, retentionality is with a 90-degree. So I'll get another movie. I have a lot of movies now. So basically, you can always see. Wait, I need a bigger. Here we go. No, I need a bigger box. oh, I need a bigger box. So this is a bigger box. So generally, you can always see three sides to a three-dimensional object, right? There's always a front, side, top, bottom, left, and right. There's the thickness, which is illustrated by these boxes. Okay, so now with that out of the way, we describe each reality or each dimension using 90 degrees geometry, right? So the smallest unit of retention is a point or a vert or some other undefined zero-dimensional or one-dimensional analogy for retention. 2 points define a line, which is usually defined as the first dimension. From 2 lines, so if you get a line going this way and a line going this way, the space in between will give you a plane. From a plane, you can expand the plane outward, and then you can define the three-dimensional geometry of a cube, which was the stack of DVD covers or cartridges or containers or whatever value you want to use to define them. So 3 dimensions, a bunch of planes define the three-dimensional volume, right? So you have length, which can be measured with the ruler. Length gives you area, and then area gives you volume, right? These are the most fundamental understood things in our science of geometry and measurements of our spatial retention or spatial dimensions. Spatial dimensions is an acceptable terminology. However, we use time to describe the 4th dimension, which is why I prefer retention. Because the 4th retention, while it is temporal, and what I mean by that is we live in a three-retentional space with a 1 dimension of time, which gives 1 dimension of temporal, which gives us our 4th retention. So the 4th retention really basically is just the perceived reality that we operate in. However, we are best analogized as 3rd retentional entities because we don't have full capacity to understand the highest dimension of our temporal. We don't perfectly embody the highest dimensionality of our retention, of our 4th retention, which will be temporal, as the analogy goes. The analogy I'm going to give you is not temporal based. I'm going to explain the 4th geometric retention. I could go into the time thing, but we'll say that for another video. The 4th retention. Now, everyone knows about the space-time analogy for our universe, which I personally don't like. I don't disagree with it, I just don't like it. I think that it doesn't perfectly serve to illustrate space-time in a way that helps you to understand the nature of reality. So, all objects, right, come in different sizes and shapes. The volume of a okay, how do I want to set this up? The volume of a sphere. Alexa, how do you calculate the volume of a sphere?
Sorry, I don't understand.
Alexa, what is the volume of a sphere?
The volume of a sphere is equal to 4/3 times pi times the radius cubed.
Which she said. So basically, okay, we'll use a cube because that's easier. Alexa, what is the area of a cube?
The surface area of a cube is equal to 6 times the square of one of its edge lengths.
6 times the square. Yeah, that's right. 6 times the square of one is actually. Usually you, Wikipedia. Hold on. I want to give you a more concrete answer, and it's been a while since I looked this up. I just need to see it. Okay, now that I can see it, the area of a cube of a sphere is 4 pi r squared. That's all I needed to know. The area of a circle is 2 pi r squared. So, a circle requires 2 dimensions, right? You need a length and a depth to draw a circle and calculate the area. But if you notice, the area of a sphere is 2 pi r squared, and the area of a circle is 2 pi r squared, and the area of a sphere is 3 pi r squared. Let's look at the area of a square. The area of a square. The area of a square is side squared. The area of a cube is side cubed. I should know that off the top of my head, but I've been working a lot. So, the area of a square is the side squared, and the area of a cube is the area cubed. So the area of a line should, by definition, be just the line raised to the power of 1, which would just give you the length of the line. The reason why I wanted to use those analogies is because the way that you understand the fourth retention is by realizing, and okay, now this is going to be a stretch because everything you have been taught, right, up until this point has been rigidly pounded into your brain so that you will be conditioned to think exactly the way you need to think so that you can function in a way that is applicable to society. So I'm going to say something that you're going to immediately be like, well, that's wrong. But it's not. It's really not wrong. It's actually it's exactly the way nature has described it and exactly the way that we perceive it. We have just been conditioned not to understand it in that way. Just like chemistry is the study of the valence shell electrons orbiting around an atom, and nuclear physics is the study of the structure of the atomic nucleus of an atom, but we should just call it nuclear chemistry because it's still chemistry, it's still the interactions of the atomic particle. That's kind of what I'm about to speak on now. It's not wrong to say nuclear chemistry. You've just been given an entire field of science outside of normal chemistry to justify the need to write 600-page books on what should otherwise be a footnote inside of the field of chemistry. Footnotes, that should be plural. There's a lot of extra stuff that should be added to those books. But I digress. Okay. If you have I'm going to use the analogy of a circle because it's going to work very well for going into the space-time fabric. The volume of a circle is a fixed amount of space, right? So you can take matter, you can put it in the volume, right? So imagine this: if you take this room has a fixed volume, right? If you divide this room up into even quantities, if you divide this room into even quantities, so you have specific volumes. So you can just grab a volume here, put it here, grab a volume here, put it here, and you have 2 volumes of this room in front of you. If you look at the periodic table elements, and I don't have any other way of explaining this, if you put hydrogen in this container and helium in this container, you can get a fixed amount of volume. You know what? Let's not use that because gases fill their containers. Let's say water. You put water in this container and water in this container, you will have the exact same equal volume of water in both containers because both containers may have the same volume. Correct? Correct. Okay. Because that's the analogy we're going with. So, with that understanding, if you take, let's say, vegetable oil and water, and you fill these 2 containers and you measure them, they're going to have different weights, right? Their different weights is a measurement of their density, right? Now, here is the fourth retention. A volume is fixed. You can only put so much water in a specific volume because the volume itself is fixed, right? If we understood the fourth retention. We could pour more water into a volume and change the density of the water. The density of every material, every gas and element on the periodic table is fixed. We don't know how to change that. The densities are fixed. The amount of volume they take up is fixed. Those are fixed values that we can measure. However, the density of a material is also its fourth retentional volume for that space-time. So what I'm saying is, what I'm applying is every physical dimensionality, length, width, and depth, the fourth 90-degree angle is the actual density. We define it as density, but that is the fourth value of spatial retention, because there is a higher dimensional interaction taking place that all the matter and materials of our universe interact with to give us those volumes. Think of it this way. You have perimeter, you have area, you have volume, and you have density. Density for every material is absolutely fixed. But you can only put so much volume in an area, and you can only currently put so much density in an area. Because when you put X amount of water into a container, the density of that water is absolute to that container. If you put X amount of lead in a container, the density of the lead is absolute to the volume of that container. If we as humans figure out a way to change the density of chemical elements, then we will understand the fourth retention. Because density, as we know it, is linked to the protons, neutrons, and electrons. But we do know for a fact that bodies like the sun and the earth can have fixed volumes and varying gravitation. The gravitation of celestial bodies is defined by their density. Well, the gravity of volumes is defined by their mass, but their mass is a direct reflection of their density. So when you see the little space-time analogy of the balls rolling around on the universe and the little plane that I don't like, and then they show the little indentation underneath them to illustrate how they warp space-time, technically that's illustrating the fourth retention. It's literally illustrating that volume of the fourth retention. If you have a sphere that's fixed in space and you draw a two-dimensional plane underneath it, you've just defined another dimension to describe a new dimensionality of that geometric structure. And when you put this idea of this spatial hole under it, this curving of the two-dimensional plane, you're illustrating what the fourth retention looks like. You're illustrating how that volume is affecting the fourth space-time analogy, because you can't emphasize that there's more matter in that volume than there is, because our minds are limited to that. But we can measure it, because that's science. That's what makes it a science. That's what makes my analogy of the fourth retention more absolute and concrete than just saying it's a 90-degree angle off of the other 90 degrees, because we can measure the fourth dimension. We can measure the fourth retention. And I can rant and ramble for another 20 minutes to keep putting analogies on analogies, but there's no need to. As always, my name is Paul Emerson, and that's my 2 cents. And if you have any suggestions for videos or other topics that you would like me to answer or suggest, or would like to suggest that I do, please add them to the comments in the comment section, and I will get to them in as timely of a manner as I possibly can.